The second derivative. So far, the functions that we've looked at and we've been studying, we've used to find the first derivative, the rate at which the original function was changing. But we could also take that same analysis and perform it on the first derivative to get the second derivative. The derivative of a derivative is called the second derivative of a function. The second derivative is a function in itself, and it describes how the derivative function is changing. So the notation that we use for this, most of the time, is going to be f double prime of x. So again, that's Newtonian notation. We're going to use 2 tick marks to indicate the second derivative. Similarly, if we wanted to use Leibniz notation to study something like the units or to talk about things that are impacting the derivative, we would write that as d squared y over dx squared. So it's the second derivative of y with respect to x. The only time we've seen second derivatives so far is when we looked at the example of position in the last lecture. So remember, position we usually write as s of t. The first derivative of position we said was velocity. The second derivative of position, which is the first derivative of velocity, is called acceleration. So second derivatives have implications. If you think about driving, s of t is your position at any time. Your velocity is how quickly your position is changing, so something like 50 miles an hour. But your second derivative is how quickly the rate at which you're driving is changing. So if you're going from 50 to 60 miles per hour, that means you are accelerating. Whereas if you go from 70 to 40, you are decelerating because you're slowing down. So even though your position is still moving in the positive direction, the rate at which your car is moving is slowing down. So the second derivative gives us some insight into how the rate of change is changing. Consider now another example to motivate why the second derivative will be useful for us. Consider the following scenario. A boat off the Gulf of Mexico has reportedly begun leaking oil. The first derivative would tell us the rate at which the oil is leaking from the boat. Now, we expect the function to be an increasing function because we're going to be measuring the amount of oil that's leaking out of the boat over time. And that's going to be going up and up as more and more oil leaks out. However, as the oil is leaking out, the hole that it's leaking through is also getting bigger and bigger. It's growing because the force of the oil is making it grow. Therefore, the rate at which the oil is leaking out is also changing. So if we measure the rate at which the rate is changing, so how much it's growing as the hole gets bigger, then we're using the second derivative. Now, this is important because we're trying to figure out how to stop the leak, obviously. And we want to know how quickly that rate is changing to determine the types of impacts and how much time we have to actually stop the leak. So there's a lot of implications of the second derivative and looking into how quickly the rate of change is changing. We're going to look at some examples to motivate the second derivative and look at how we can study this and the relationships between the original function, the first derivative, and the second derivative. In this section, we're going to be building off the key relationships that we started talking about earlier in this chapter. So remember, if f of x is increasing on an interval, then the first derivative is positive on that interval. If f of x is decreasing on an interval, then the derivative is negative on that interval. And if f of x is constant on an interval, then the derivative is 0 on that interval. We did this by plotting tangent lines and looking at the relationships, and we said that the slopes of those lines are related to whether or not the function is increasing or decreasing. So starting with this idea, let's look at an example. Example 1. Consider the function f of x below. Determine the intervals where the first derivative of this function is positive, negative, and 0. So again, if we want to talk about where the derivative is positive, negative, and 0, we need to determine where f of x is increasing and decreasing. So here, I'm going to start by looking for where we are increasing. So it looks like this function is increasing when we start reading from left to right. So I'm going to say that this function's increasing from approximately negative 2.75 until 0. Now, if you wanted to use negative infinity to 0, that's fine as well. We can assume that the function goes on and on forever. However, since there's not arrows at the end, I'm more comfortable using the actual cutoff point. Now, I'm using open parentheses because, again, I'm not including the endpoints because I don't know exactly where that function ends. And at 0, that's where my function is constant, so it's not considered increasing there. I'm also going to be increasing over here on the right end of the function, right at the tail. So it looks like I'm also going to be increasing from 4 to 5. So again, when my original function f of x is increasing, that tells me the intervals where the first derivative of that function is going to be positive. So that's the first thing I needed to look for. I'm also interested in where the first derivative is negative. So again, I need to consider where this function is decreasing. So looking at this picture, I can see that I'm going to be decreasing from 0 to 4, right here, this interval here. So that means from 0 to 4, the first derivative of this function is going to be negative. Finally, I want to know where it's going to be 0, that first derivative. And we said we're going to be 0 when the function is constant or where we have horizontal tangent lines. So that means we are going to have the first derivative equals 0 when x equals 0 and x equals 4. So again, that's the place where we change from increasing to decreasing or decreasing to increasing. And again, those are places we have horizontal tangent lines. So now we've determined where the first derivative of this function is positive, negative, and 0. We're going to take this a step further in example 2, and we're going to try to graph the first derivative of this function next to this particular function. I would encourage you to pause the video here and try graphing it on your own before you watch the solution. Example 2. Given the graph of f of x, sketch the graph of f prime of x. So f of x is a function we were looking at just a minute ago, and we wanted to sketch the first derivative. So this is what the first derivative is going to look like, and let's talk about why. So we said that we're going to have a horizontal tangent line at 0 and at 4, which means my function needs to pass through at 0 and 4. Those are the zeros of my function. Now we said we were increasing from negative 2.75 until 0. And if we're increasing, that means we need to be above the x-axis. We need to be positive. We also said the derivative would be positive from 4 to 5. Then from 0 to 4, my function was decreasing. And if my function is decreasing, that means my derivative needs to be negative. So here from 0 to 4, I was decreasing, which means I need to be below the x-axis here. I get the general shape from the graph by looking at slopes of various tangent lines to try to match up where approximately they'll be. But in general, my derivative function should look like a u. Example 3. Consider the function below. Determine the intervals where the derivative of this function is positive, negative, and 0. This is very similar to example 1. Only now we have a new function that we're looking at, and this new function is exactly the function we got when we took the first derivative of the original function before. Only now this has become our original function, and we want to talk about the derivative of this picture. So here, if we want to know where we're positive, negative, and 0, we again are going to look at where our function is increasing and decreasing. So my function here is going to be increasing to the right of 2. So at 2 is where I turn around, but from 2 to 5, this function is going in the upward direction, which means that the derivative of this function is going to be positive from 2 to 5. This function is going to be decreasing, if we look over here on the left, from about negative 2 until 2. So we're going in the downward direction here. So therefore, on that interval, the derivative of this function is going to be negative. And then we're going to have a 0. The first derivative equals 0 at the point where we change from increasing to decreasing, where we also have a horizontal tangent line. That happens at x equals 2. So again, I can talk about the derivative of this function in terms of positive and negative by looking at where this function is increasing and decreasing. It's really important that we understand that increasing and decreasing are different evaluations than positive and negative and what those differences are. Now, again, we're going to take this function and we're going to try to draw the derivative of this function based on the information we have here, where it's positive, where it's negative, where it's 0. So I would encourage you to pause the video here and try to sketch out the first derivative before you watch the video. Example 4. Given the graph below, directly below, sketch the graph of its derivative. So again, we said that we're going to have a horizontal tangent line right at x equals 2. That's where we changed from increasing to decreasing. So we have a 0 there. We said we were decreasing from -2 to 2, which means we should be below the x-axis. We should be negative, which we are here. So decreasing in the original means negative in the derivative. And then we're going to be increasing from 2 to 5, which means we're going to be above the x-axis. And again, we talked a little bit before about this U-shape and how it translates into a rough increasing function that goes to the 0 where we have the horizontal tangent line. So the derivative of that U function is roughly linear and looks like the graph on the right. So congratulations, you've just done your first second derivative. Now don't get confused, it's the first one you've done, but we've made it to the second derivative because we started with an original function and we took the derivative to get that U-shape. And then we did the same analysis on the U-shape to get the derivative of that, which was the linear function, which means that this function on the right is the second derivative of the very first graph we looked at. Now, because we did the analysis the same way, we can add to our set of rules about the relationships between these types of derivatives. Since the second derivative is the derivative of the first derivative, the same rules that we applied to the original and the first derivative will apply here. So, if f prime of x is increasing on an interval, then the second derivative is positive on that interval. If the first derivative is decreasing on an interval, then the second derivative is negative on that interval. And if the first derivative is constant on an interval, then the second derivative is 0 on that interval. So the same analysis we can do on any function to get the derivative of that function. Now, we have a relationship between the original and the first derivative. We've now established a relationship between the first derivative and the second derivative. It's the same relationship. But what we don't have yet is a relationship between the original function and the second derivative. So let's take a look at their pictures and see if we can figure anything out. Example 5. Consider the graph of f of x and f double prime of x given below. So we have the original and the second derivative. See if you can determine a relationship between the original function and the second derivative based on their graphical properties. So I want to remind you of the 3 graphical properties we use to compare things. We've done increasing and decreasing as one set of properties, positive and negative as another set of properties, and concave up, concave down as the third set of properties. So those are the ways we describe graphs. So those are the things we're looking at here to see if there's a relationship. So if you haven't already identified it, I will tell you that the relationship is between the concavity of the original function and the sine of the second derivative. So here, if you look at the original function, we're going to be concave down. Concave down looks like a frown. We're so sad. All over here, CC down. And then to the right of 2, we're so happy, like the smiley faces from the 90s. We're going to be concave up. So if you look at the second derivative, you'll notice that to the left of 2, our function is negative, But to the right of 2, our function is positive. So that means if the original function's concave down, the second derivative is going to be negative. And if the original function is concave up, the second derivative is going to be positive. Now, right at 2 is where we change concavity. And this point has a special name. This is called an inflection point. And the inflection point, again, is where our function changes concavity. And that means on the second derivative, that's going to be where we equal 0. Because right at that point, we're not concave up or concave down. It's where we're changing. So now we have the relationship between the original function and the second derivative. So now we have a comprehensive set of relationships between the original function, the first derivative, and the second derivative, and we can use these to analyze all sorts of things, graphs and tables and functions. But what's really important is that we keep all these relationships straight. It's really easy to confuse things like positive and negative and increasing, decreasing. So it's worth your while to try to remember all these relationships, whether it's through memorization or ample practice of practice problems. These are going to serve us for the rest of this course, and it's really important that you understand them well. So again, if f of x is increasing, then the first derivative is positive. If f of x is decreasing, the first derivative is negative. If f of x is constant, the first derivative is 0. If the first derivative is increasing, the second derivative is positive. If the first derivative is decreasing, the second derivative is negative. If the first derivative is constant, the second derivative is 0. If f of x is concave up on an interval, then the second derivative is positive on that interval. If f of x is concave down on an interval, then the second derivative is negative on that interval. And if f of x is at an inflection point, then the second derivative equals 0. Now you'll notice that there's an asterisk on the very last rule. All of the other rules work in both directions, right? So for example, we have if f of x is increasing, the derivative is positive, which also means that if the derivative is positive, we know that f of x is increasing. It works in both directions, and that's true for all except the very last statement. So if f of x is at an inflection point, then the second derivative equals 0. However, if the second derivative equals 0, it's not necessarily an inflection point. We'll circle back to this when we get to a further chapter, but the asterisk is there now to keep that in your mind, that that's the only relationship that doesn't work in both directions. So now that we know a little bit about the second derivative, let's go ahead and do this particular example to help us see the differences between original functions, first derivatives, and second derivatives. So use the function below, which is f of x, to determine if the following quantities are positive, negative, or 0. So we're going to start by analyzing what's happening at negative 2. So the first batch that we're going to look at, we're going to consider what's happening at negative 2. So that's the point at negative 2. So f of negative 2 is the y value when we plug in the x value of negative 2. So we're just trying to determine if the function is above or below the x-axis when x equals negative 2. That y value is going to be negative because it's below the x-axis. So f of negative 2 is negative. F prime of negative 2, the first derivative, is going to consider whether or not the slope of the tangent line is positive, negative, or 0. We can see that we're decreasing there, and a quick sketch of the tangent line also helps us see that the first derivative is going to be negative because the slope of that tangent line is negative. Now the second derivative at negative 2 is looking at the concavity at negative 2. So I'm drawing in the inflection points here just so we can see where we change concavity. You'll get good at finding those as our chapters move along. But here, between roughly negative 2.5 and negative 0.9, this function is concave up. So here at negative 2, this function's concave up. It looks like a cup. And if your original function is concave up, that tells you that your second derivative is positive. So we can analyze three different things at one point on a graph. One by looking at whether it's positive or negative, one by looking at if it's increasing or decreasing, and one by looking at if it's concave up or concave down. Let's practice this at the other points. So now we're going to move on to see what's happening at x equals 0. So at x equals 0, we're going to be up here at this point right up here, right about 1. So f of 0 is asking about the y value when x equals 0. The y value is going to be positive 1. It's above the x-axis, so that value is going to be positive. The derivative at that point is actually going to be a horizontal tangent line because that's the place where we change from increasing to decreasing, which means the derivative at 0 is equal to 0. And then the concavity, we can see here, this function's concave down right at 0. So if we're concave down, that means that the second derivative is negative. Similarly, we can do the same analysis at 2.5. So 2.5 is roughly here. So again, we start by analyzing whether or not that point is above or below the x-axis. That's certainly above, so f of 2.5 is going to be positive. The derivative here is also going to be positive. The function's increasing, and if we draw on a tangent line, it's going to be positively sloped. And then we see that it's concave down, because between the 2 points, it's downward curved. So it looks like a frown or a hill. So since we're concave down, the second derivative is going to be negative. So we should be able to take any graph that anyone gives you, pick a point, and determine at that point if the function is positive or negative, if the derivative is positive or negative, and if the second derivative is positive or negative based on the properties of the graph. And that's something that we will do quite a bit throughout this course. So far, we've been doing most of our analysis on graphs, and graphs are something we're going to spend a lot of time with in this course, but I want to show you that we can also apply some of these rules to our tables. So example 7, given the tables below, determine the intervals where f of x is most likely concave up and concave down. We've actually done this before, back when we looked at average rates of change. We talked about how concavity is based on whether average rates of change are increasing or decreasing. So for our first table, we have x and f of x values. So this is your typical function. So that means we can use average rates of change to study the concavity. So remember, average rates of change are going to look at change in y over change in x. So here, between 1 and 2, the change in y is 3 minus 1 divided by 2 minus 1. That's going to give me an average rate of change of 2. Between the next 2 points, I'm going to do 6 minus 3 divided by 3 minus 2. And that's going to give me 3. And then I'll do 10 minus 6 divided by 4 minus 3. And that'll give me 4. And then 13 minus 10 divided by 5 minus 4 will give me 3. 15 minus 13 divided by 6 minus 5 will give me 2. And 16 minus 15 divided by 7 minus 6 will give me 1. So if I look carefully at this, I can see that my average rates of change are going to be increasing from 1 to 3. And then they're decreasing from 4 to 7. So that means, again, when your average rates of change are increasing, that means that your function is concave up. That's the same thing as when our first derivative is increasing. Since our average rates of change approximate the derivative, if the average rates of change are increasing, then the instantaneous rates of change are going to be increasing. And therefore, the first derivative is increasing, which tells us that we're going to be concave up because the second derivative will be positive. So here, from 1 to 3, our function is most likely going to be concave up. And then similarly, from 4 to 7, our functional values here that we've calculated using average rates of change are decreasing, and therefore we expect our function to be concave down. Now, somewhere between 3 and 4, we're going to have some sort of inflection point, because we're changing from concave up to concave down. We don't know exactly where it is, but if we were to guess where the inflection point was, we would guess between 3 and 4, because that's where we've changed from concave up to concave down. Now, in our second table, I want you to notice that this is not x and f of x. Instead, we have a table that gives us x and then f prime of x. So that means that the values that are being reported in this table are the values of the derivative, or the instantaneous rate of change at each of these points. So now we're going to go to that relationship that said if your derivative is increasing, then your second derivative is going to be positive. So let's look at where we're going to be increasing here. So 2, 5, 6, 12, 17, those are all increasing values. If your first derivative is increasing, your second derivative is positive. That's the relationship we have. But we also know that if the second derivative is positive, that the original function is going to be concave up. So we know that from x equals 1 to x equals 5, f of x, the original function, is going to likely be concave up. Similarly, if we look at what's happening from 5 to 7, we see that those values are decreasing. 17, 14, 11. That tells me that the second derivative is going to be negative. And if the second derivative is negative, that tells me that the original function, f of x, is concave down. So trying to keep all these graphs straight can be difficult. So I just want to remind you, for all of these that we've just looked at on the tables, we're talking about what's happening on f of x, the original function. So when we say that it's concave up on an interval, that's the interval on the original function. We're not talking about the concavity of the first derivative or the second derivative. We're talking about the concavity of the original function. And we're using the first and second derivative to approximate where this concavity would be concave up and concave down on the original, using the relationships that we have between the functions.